Hi everyone. So today, whenever you guys are watching this, we get to start Chapter 8 in Thomson, and this is the chapter on deep inelastic scattering. We're finally able to actually probe inside the proton. So it's a pretty neat chapter. That's why I wanted to cover it in detail. So we're in the previous chapter, right, we treated the proton. So the proton is a point particle with some charge, right? That's the low energy or low q square, or the wavelength of the exchange photon is so long that you don't actually notice the structure of the proton. In the end of last chapter, we started probing the the charge coupling and the magnetic spin coupling of the proton between the proton and the electron, because they're both spin 1/2 particles, and so therefore as they move relativistically towards each other, there is a magnetic coupling between them. In this chapter, finally, what we're going to do is we're going to actually see what's inside the proton. And this is probably not a surprise to you guys, but let's say in the middle to late 1960s, when people were colliding electrons and protons together, they were really confused of what's going on in there, right? Because people had no idea what's actually inside the proton. And and nowadays, for you guys, is quarks and gluon. So what we're going to do is we're going to define a few kinematic variables first in this section, and then we're going to dive into how the interactions inside a proton actually occurs if you just have a electron interacting with it. So this is still quantum electrodynamics because we're still exchanging the photon. But then we're going to start seeing, okay, what's going on with all these gluons and quarks interacting with each other inside the proton, and therefore things get a lot more complicated, and therefore we don't actually do a lot of calculations on it. We just run an experiment in order to determine these things. Okay, so one of the first things that we should talk about is that as you increase the energy of the photon that's being exchanged between the electron and the proton, I'm putting in quotes the proton, okay, what's going to happen is that there's going to be enough energy. So in this little kinematic diagrams here, right, you have an electron, you have a proton. This is actually what's usually happens. Actually, you have the electron and the proton running into each other like that. But this just simplifies the exchange of these things, where you have this photon exchange between the proton and the electron, okay? And what happened is that this photon is so energetic, it actually starts to break up the constituents of the proton. You just break the proton up, and it'll reform itself in some other ways. But what happened is that when the proton breaks up, right, it actually breaks up into other hadrons, and hadrons meaning anything that's made of quarks, right? So U bar, right, that's actually a pi 0, right? And then a proton, right, is up, up, down, and then a neutron is up, down, down. So all of these are hadrons, right? So they would have each of these have different masses, right? Specifically, more importantly, right, the mass of the proton, right, coming in here, and then the particle that's coming out, and they're just going to label this, capital X, right? Since we're making new particles, right, what's going to happen is that the masses of all these outgoing particles is going to be bigger than the protons, because you basically just added energy into it, and some of that energy gets converted to mass. Okay, so what we're going to do is we're going to quantify this lump of stuff, the form momentum of the outgoing spray of particles, spray of X particles, right? So that's the form momentum P4. Okay, we're going to call that W instead. Okay, just to make it a little bit clear, it's actually a jumble of different particles that's actually going into this. Okay, calculation only, right? That's just P2 plus whatever Q is, right? So if you have Q coming in here, you have P2. Conservation momentum tells you that, well, P2 plus Q equals to P4, and then if you square that, right, then you're going to have the mass of the of whatever particles we're talking about. Okay. So yes, I know that, right? P4 is not just the proton anymore. I'm going to make the line a little bit thicker here. Okay, it's not just the proton anymore, right? It's a combination of many particles. So the 4 momentum squared, right, whatever this value is, okay, right, it's actually not just the mass of the proton, it's mass of a bunch of other things, okay? Specifically, what's going to happen is that P4, right, is the 4 momentum of, some particle A, some particle B, some particle C, right? Let's just mark them here, right? Some particle A, some particle B, some particle C, some particle D, right? All that stuff comes out, right? In order to calculate what the 4 momentum is, you have to add them, right? Because this is the energy part of particle A, right? Gamma A, MA, all come at different speed also, and therefore the gamma factor is different between them, okay? And then you have the same thing for B, you have the same thing for, well, I didn't type C, and then you have the 3 momentum part of these particles also, right? Determined by gamma A, MA, VA. Don't worry too much about the details of this. We're going to try to do this in a Lorentz invariant form anyway, okay? But that's physically what you want to picture. You have a bunch of particles coming out, and each of them will have its own 4 momentum, but when you add all of them up, you will get, the 4 momentum of the outgoing particles summed up together, okay? To make this a little bit clear, the book decided to call this W, okay? All right, since this is still a T-channel process, right, you're still exchanging this photon between your 2 incoming and outgoing particles, okay? This Q square is always going to be negative, okay? So therefore, right, just like what we did in chapter 7, we're going to define that, well, a capital Q square equals to the negative Q square, okay? Okay, so since Q square, well, Q itself, right, is P1 minus P3, right? Therefore, right, capital Q square is Q square with a negative sign. Therefore, you square this and then you put a negative sign in front, okay? And if you just do a few steps of algebra, what you will end up with is that you're going to get twice the mass of the electron, and then E1 times E3, and then the magnitude of the 3 momentum of P1, P3, and the angle between the incoming and outgoing particles, okay? Once again, what we're going to do is since the mass of the electron is so small, we can ignore it, right? And that's going to tell us that, it's 1, this is going to be 2 times E1 times E3, 1 minus cosine of the angle between them, where, P1 and P3 basically going to be energy 1, P3 is going to be basically energy 3, because, right, in this, if you can ignore the mass of the electron, right, the energy and the momentums are the same. And this is where we come up with, right, just as, we did the same equation in chapter 7, right, where, this 1 minus cosine becomes basically a factor of 2 with a sine square theta over 2, right? That's where the sine of theta over 2 come from in the Mach cross-section, right? Sorry, in the Rutherford and the Mach cross-section. Okay. Actually, that's wrong. Yeah, only in the the recoil scattering, you have this sine square theta, okay? The Rutherford one actually comes from a different reason, okay? Okay, so, right, this Q square, right, can have range of, electron volts square, GeV square, TeV square. So it would be nice if we can kind of normalize it somehow. And, this is kind of us knowing this is, Thomson and probably me also, knowing what the answer is going to be and then justifying why the path we went there. But in the 1960s, people did not know any of this stuff. So therefore, a lot of people were just trying different combinations of calculations. But what we're going to do is we're going to define something called X, okay? And this X is going to be very important. It's basically one of the main points of this chapter is for you guys to understand what this X is and and I'll tell you what the answer is, but so if you ever read a particle physics book, you already know what this is. This is basically what's known as the parton distribution for a particular, hadron. Okay, and what this x tells you is that what fraction of the momentum is carried by the up quark, what fraction of the momentum is carried by the down quark, what fraction of the momentum is actually carried by the gluons. The gluons also carry momentum because it's part of the proton. Okay, right? And with a little bit of algebra, you're going to see that, well, we can define this x as q squared over q squared plus w squared minus the mass of the proton squared in the proton case. Okay. Since w squared is the invariant mass of all those outgoing hadrons, right? And remember, all those outgoing hadrons is going to have more mass than whatever the proton started with, right? Therefore, whatever this factor here is going to be positive, right? It's some positive number, okay? Right? And therefore, let's say, right, w squared is basically approximately mass of the proton square, right? In this case, right, x is going to be equal to q squared over q squared plus basically something that's almost zero, right? Because they're so similar to each other. In this case, x is just going to be approximately 1, okay? Right? So, okay. In the case where, right, the outgoing particles mass is basically the mass of the proton, meaning you did not make new hadrons, okay? We actually go back to the elastic limit where basically the entire momentum is carried by just the proton itself. We don't have to worry about all the stuff inside, right? And therefore, x is actually equals to 1, okay? Well, however, right, if w is much bigger than the mass of the proton, okay? So you have a x q squared over q squared plus a big number, right, squared, right? And therefore, like 1 over a big number squared is going to be approximately 0, okay? So as the mass of the outgoing hadrons increases, or you're making more and more particles, right, this x is actually going to get smaller, okay? All right, so this is known as the elasticity parameter in this section because it tells you how elastic that collision is, right? Remember, when x is 1, you basically have elastic collision. When x is 0, you have a completely inelastic collision. Okay, and we're going to see what this also tells us about the structure of the proton later on. All right, so now let's see if we can quantify an inelasticity parameter. Okay, an inelasticity parameter is defined as the mass of the proton. Well, these actually cancel out, right? If you do a little bit of math, then you see that this is actually 1 minus E3 over E1, okay? The reason this is called the inelasticity parameter is that, well, if in elastic collision, right, let's say you have, right, E3 is going to be approximately equal to E1, right? Going back to chapter 7 again, right? When we had Mott scattering and Rutherford scattering, those are completely elastic scattering. So therefore, E3 is actually exactly equals to E1, right? There's no recoil from the proton, okay? In this case, right, what will happen is that, well, this factor turns into 1, so 1 minus 1 is 0, so therefore you actually get 0, okay? Right, hopefully this makes sense to call this the inelasticity parameter. But, right, when E1 is much bigger than E3, okay, right, so therefore this y parameter, let's go down here, right, it's 1 minus a E3 minus over E1, right? If this number is big, right, then therefore this term goes to 0, y actually becomes approximately 1, right? So therefore, right, when you have very inelastic scattering, this parameter goes to 1, okay? So they kind of have opposite behaviors from each other. If that's not enough, we're going to also find a new variable called nu. It's actually related to x and y, but it's sometimes useful, and we'll see how useful this is. Okay, this parameter nu basically tells you how much energy is lost, okay, by the incoming electron. Okay, nu is just E1 minus E3. Okay, but another way to write this is actually P2.Q, so that's the outgoing electrons, the protons for momentum dotted into the photons for momentum divided by the mass of the proton. Okay, and this is the full list of all these variables that we just defined, and we're going to be using these in this chapter in order to get to something known as to study the structure inside the proton. Okay, there are also a few relationships you can relate these variables to each other, right? So if you have Q and nu, right, you can calculate what X is. If you have nu and the center mass energy, right, you can calculate what I is. If you want to figure out Q squared and you have X and Y, you can just multiply those two together. And then if you know the center mass energy, you also can calculate Q squared. Okay, and we'll go through some homework to prove these, okay, to derive these relationship. Okay. We're going to start off thinking about is that let's do some inelastic scattering at low Q square. So we're still kind of on the threshold of like we're able to see inside the proton, but not as much detail as we want. Okay. So low energy here is about a few GeV. So, in other places, this will be extremely high energy because basically a GeV is the mass energy of a proton, right? Okay. The way people measure this is by basically, if we look at this little diagram on the right here, right? We have some beam of electron, and then we basically have a fixed target of usually like liquid hydrogen, because we want to smash them into protons, right? And hydrogen is made of protons, okay? And what happens is that the slow electron beam comes in, right? Smashes into into the proton, right? And is guided kind of like away from the collision point. And what you see here on the left here, right? This is the detector, right? What's actually drawn here. You see this upward trend. You also have this top-down view. So this is the side view. This is the top-down view, right? You can see these tracks here, right? Where these tracks allows you to rotate this detector at up to 180 degrees, right, in front of the beam. Okay, therefore, right, why are we interested in this, right? Remember that, right, the amount of energy lost by the electron, right, can be completely determined by the angle that the electrons scatter off of, right? So therefore, right, if you actually can measure, if you know the incident beam's energy, E1, and if you know not E, but the angle that the electron came out at, right, theta, you can actually completely figure out how much energy was transferred between the electron and the proton. Okay, so for example, if you have energy of the beam is about 5 GeV, and then move your detector so that's at 10 degrees, right? You can measure, right, the cross section, meaning basically how often, right, you will have events, the rate of events that you would get at this particular beam energy and at this particular angle. Okay, right? And what you can plot is this double differential cross section. The double differential cross section means, remember, usually differential cross section is just d sigma over d omega, right? But now you're plotting this as a function of energy also. So you take another derivative with respect to energy, and therefore you have a function of the cross section as a function of both the angle and the energy. Okay, and this is the result for this. I think this is from the DAISY experiment in Germany. Okay, where they measure this right, at one particular beam energy, and they put the detector at a particular angle, and then they just measure the rate, okay, as a function of how much, as the function of the outgoing electron's energy, then that tells you how much energy was actually deposited into the proton. Okay. And there's some interesting structure here, and that's why I really like that Thomson brought this up. Okay. Well, I'll start first of all. Oops. Right. Since the beam energy is about 4.8 GeV, right? Anything that's above 4.5 GeV of E3, these are all elastic scattering. Okay. Right. That's the Rutherford, your Maude, and your Rosenbluth scattering. But what happened is that as you decrease in the outgoing electron's energy, in other words, increasing in the momentum, the energy of the outgoing shower of partons, of hadrons, okay, right? So the more energy the electron loses, that energy gets dumped into making more particles in that outgoing shower, okay? As you do that, what happens is that you start to see this peak here at about 4.2, okay? Well, 4.2 doesn't really mean much, but if you keep going down, or you can convert it to basically W, you'll see something at about 1.2 GeV, okay? And why is 1.2 GeV special? If you look in this website called the Particle Data Group, which is one run at LBL, actually, if you guys go to LBL this summer, I can show you where their office is, okay? You're going to find that, well, there is a particle called delta particle, which has a mass of 1232 MeV, and surprise, surprise, right, about 1.23 GeV. Okay, and this is exactly where this peak corresponds to. It's super neat and really interesting, right? And actually, like if you look at this plot down here in the caption, right, this plot was made, right, in 1968, right? This is when people were still trying to understand what the hell's going on with all this inside a proton. Okay. All right. There are other structures here. There's another peak, right, at about 1.5, right? These are made by these capital N particles. So they're not lowercase n, which is neutron, but the capital N. They're basically kind of like, just think of these as kind of like excited states of protons and neutrons, where as opposed to just at their lowest angular momentum state, they're spinning, they have higher angular momentum, therefore they carry more energy inside them, and therefore it has more mass inside as a result. Okay. So that, this peak here, right, is pretty broad, right? And that's because you have like multiple particles contributing to them, and each of them has a slightly different mass, unfortunately. Okay. If you squint really hard, you can even see another one at about 1.7 GeV, right? And those are the ones down here, right? The N1650, the N1675, and N1680, right? Okay. So how, by looking at this plot, how did I figure out how to look at this thing, right? So I wanted to just give you guys a quick lesson on reading the PDG, because you will be using it in the future if you stay in particle physics, okay? So in the PDG, if you go to this website, actually, I'll just go to it, my mouse. I can do that. Let's minimize this, right? Okay. Over here, you can go to particle listings, okay? And in the particle listing, you can list, they give you a list of gauge boson, leptons, and quarks, and stuff like that. Those are probably easier to look at, right? You can just look at this, if you want to look at the properties of electrons, right? It tells you what the mass is exactly in MeV, right? It tells you about the dipole moment. It tells you all this information about it. Let's go back up here, right? So let's not go to the review. I want to go to particle listings. Okay, let's look at those baryons. Okay, so baryons. Remember the protons, the neutron, lambda, and all these other ones, right? Those are the baryons. Okay, so let's look at that 1232 one, right? Which is actually a delta baryon. Okay, where it has a S equal to 0. This S stands for the strangeness. That means it has no strange quark in it. I indicates what's known as isospin. We're going to talk about that a little bit next chapter, just because it's a conserved quantity of 3/2. Okay, so notice that for protons and neutrons, it has an I of 1/3, right? Where the delta baryons has an I of 3/2, so it has a higher isospin value. Okay, so this one, so the 1232, let's click on that. Oh, okay, let's not look at this version. So this is the actual text. So if you ever want to, if you're at Berkeley, you can actually literally just pick one up, and this, this page, that page will be inside one of the page here. There's also a little version of it. I don't know where my little version is. I think I gave it someone. But what they like you to use now is actually what's known as the live version, where it's a little bit less stuff thrown all at you at once, but there's still a lot of stuff. Okay, so so this I, right, 3/2, and then the JP value, so that's the parity. Let's not go into detail about those yet. Okay, so these delta baryons, right, it can either be a delta plus plus, right, which is made up of 3 up quarks, right? Remember, every baryon will have 3 quarks in it, and you can choose which combination you want. Okay, and then there's also a delta plus, which actually is basically a higher energy state of the proton, UUD. And then you have a delta 0, which is a higher energy state of a neutron, UDD. And you can also have a delta minus, which is made up of all down quarks, right, which have a charge of -1. Okay, and the reason I want to show you guys this is that, well, you have the mass here, right? Well, the mass is in this number. The reason they name it that, I don't know why I stuck at 99%. Okay, right. So the mass actually has a range to it. So some of them you will find that, there'll be some will measure the mass at 1211 or 1210, right? Where other experiment may measure it at a slightly higher mass. The other thing I want to show you guys real quick is what's known as the Breit-Wegner widths, right? The width is actually what we calculated in chapter 2 or 3, I forgot, right? That's the width, right? This capital gamma, that tells you the transition rate, right? And I'm going to get the information from here first, right? So it tells you that the width for this delta particles, which is not stable, right? So it has some decay to it. Can we figure out how long it takes for it to decay? And by knowing the width, you can, and actually they tell you the width is 117 MeV, right? And this is known as the mixed charge MeV. But if you want to say, if I'm only interested in delta plus plus, right? It actually has a different width, 112 here, right? And these are different experiment measuring these things. So if you want to get the number here, you should probably just average them, okay? But then, for example, the delta 0, right, has a slightly different width, right? But all of them are kind of hanging around 117, okay? So therefore, right, if you want to figure out how long it takes for a delta particles to decay back into a neutron, a proton or a neutron, okay, right, all you have to do is plug that width, right, of 117 MeV, convert it to GeV, right, and you can calculate the tau from it. Remember, tau is the lifetime of a particle, right? And in inverse GeV, that's 8.55, right? If you convert that number using the Planck's constant, right, to seconds, you will find that the half-life of this particle is actually 5.6 times 10 to the negative 24 seconds, so very short lifetime, right?